Hello! In this video we're going to look at our first real example of a smooth manifold, and we're going to find a smooth structure for our old buddy the circle and show that it's a smooth manifold. So what do we have to do in order to show that? Well, we have to show that the circle is Hausdorff, second countable, locally Euclidean, and has a smooth structure, right? Same drill as last time. So what do we mean by S1? So we're going to be looking at the set of all points with coordinates x, y, and R2 such that the sum of their squares is equal to 1. Okay, so to show that S1 is Hausdorff, we're going to use the fact that it's a subset of R2, right? So S1 is Hausdorff because it is a subset of a Hausdorff topology. We showed that Rn was Hausdorff in the last video. And so if we look at this picture here, sort of for intuition, you could have some greater subset from R2, and using the subset topology, we just look at where it intersects S1, and we get, for example, these two open sets. But we can play the same game as we did for Rn to show that it's Hausdorff. You pick any 2 points, and you can always find an open set in R2 that contains one of the points but not the other, and then we just take the intersection with S1, and so we see that S1 is in fact Hausdorff. And then I just stated clearly, I'm giving S1 the subspace topology. And similarly, S1 is second countable because it's a subspace of a second countable space, R2 in this case. We just restrict the countable basis of R2 to the intersections with S1. We take that countable basis here, restrict it to here, we still have a countable basis for S1's topology. So it is indeed second countable. Now we want to show that it's locally Euclidean. So what does that mean? So we need to show that there's an open cover and that the open sets in that open cover are homeomorphic to Rn. So if we look at this open cover, right, these subsets I'm calling U1, U2, U3, U4, if you take the union of them, that definitely is going to cover all of S1. And I've written them out here, and they each have their own map that is going to end up being a homeomorphism. So for this guy, where you have all the points with a positive y coordinate, you just give me the x. So you can think of that as projecting the circle down to the x-axis. And the other 3 guys follow similarly. The inverses are given here, and to find them, I used the defining equation for the circle, x squared plus y squared equals 1, and paid attention with the appropriate signs. Now notice that all the phi i's are bijective and bicontinuous on their domain. That's the important part, right? We don't have to worry about, for example, x squared becoming greater than 1, and then having to think about what's going on with the square root there, because on the domain that doesn't happen. Okay, so phi I are homeomorphisms. So since S1 is the union of these 4 open sets, they form an open cover of S1. So for all points in S1, there exists a homeomorphism that maps that point to R1, which means S1 is locally Euclidean and of dimension 1. If we look at this collection of charts, those 4 charts, the open sets and their maps, is that set an atlas on S1? That's the next question. So to start, notice that phi 1, phi 2, and phi 3, phi 4 are vacuously smoothly compatible, or C infinity compatible, because the intersection of their domains, right, these open sets, are both non-intersecting. So quickly, if we come back to these, right, so if we look at U1 and U2 and we take their intersection's empty, right? They don't even meet at the points where x is minus 1 and 1. Right? These are open sets. They don't include those boundary points. And if 2 chart maps don't share any points in their domain, we say that they're smoothly compatible. So those guys are smoothly compatible, so that's taken care of. That's sort of one case for these open sets. And the other case is where the open sets do intersect. So we're going to look at the first quadrant, because I like positive numbers. And so to do that, we're going to look at the open set U4 and U1, where they intersect, x and y both are positive numbers. And now to show that, we have this region right here. I just drew us a nice picture so we can understand the information a little better. So what the heck is going on here? We've got our circle, we've got our open set that we care about, U1, U4, and then we've got our chart maps. We've got phi 4 going over here, phi 1 going over here. I kind of wrote them to respect the fact that they're projections, right? So phi 4 is going to give us the y values when we project this onto the y-axis, which is why I drew it vertically. You don't have to do that. That was just for flavor. And similarly, Phi1 projects us down on the x-axis, so I drew that horizontally. And the domain for our inverses are both from -1 to 1. And I found that just by looking at where our chart maps map our points down to. Like, so Phi1 on its domain just projects down to the x-axis to where? Well, all the points in between -1 and 1. And it's an open set, so we don't include the boundary points. And you get the same thing for Phi4. So those are going to be the domains for our inverses. I kind of hand-waved over that a little bit earlier, so here's the detail of what I was talking about, why we know those functions are going to be homeomorphisms. Now, to show if two charts that do share an intersection are smoothly compatible, or CK compatible, when we're trying to figure out what that K is, we look at the composition of one with the other's inverse. As an example, I'm going to show this one. So restricting Phi1 and Phi4 to their intersection, we see that they map down to a smaller interval, the interval between 0 and 1 and 0 and 1. So that is going to be the domain for our transition function. That's what this is called, the transition function, because it transforms your coordinates from the first coordinate system to the fourth coordinate system. But the really nice thing about this is it maps from R to R. We know how calculus works on maps that go from Rn to Rn. So we can just look at this and use our understanding of real analysis and real functions and have a very clear understanding of what its differentiability is. So if we actually work that out, we get some hopefully familiar functions. So Phi1 inverse takes in some variable and spits out for the first component that variable, and for the second component the square root of 1 minus that variable squared. And when we actually compose Phi4 with Phi1 inverse, we get Phi4 of this guy, and then Phi4 just says, okay, give me back the second component, right there. So that's what our transition function is. This guy is this guy. And just like we were talking about earlier, its domain is from 0 to 1. Since this function is C infinity, this function is smooth on the interval 0 to 1, Phi1 and Phi4 are smoothly compatible. That's what it means. So all the other calculations follow very similarly. This is an illustrative example, but that's everything you need to understand all the cases. Like either they're vacuously smooth or it follows this same procedure. Then we showed that A, the set of these four charts, is a smooth atlas on S1. It is going to be contained in some maximal atlas, which we call the smooth structure. But by knowing this atlas, we know how S1 is going to behave with any of the other charts in that smooth structure. What I would like to do in another video, I don't know if it'll be the next one or not, but I would like to look at another set of charts that make S1 a manifold and show that this other atlas is actually contained in the same maximal atlas as this one. And so they both give the same smooth structure to S1. So that's everything we needed to show that S1 is a smooth manifold. And hopefully this example made some of those ideas seem less abstract, maybe helped you get a better handle on it. I'll see you guys in the next video, and thank you very much for watching.